Okay. In this video, we're going to talk about inverses and how to compute them. So, uh, a matrix B is called an inverse of a matrix A if B times A equals A times B equals the identity. So here, A and B are both n by n matrices, and the identity is like n by n identity matrix. So that means it's ones along the main diagonal and zero everywhere else. So a 2 by 2 matrix A, B, C has inverse uh, 1 over its determinant. And then we switch D and A and negate negative B and C, or negate B and C. So, you know, like we can check that this is the actual inverse. So, so this inverse. So A times negative like A inverse is B D 1 over the determinant. Uh, so D A negative B negative C. So uh this is just a scalar, so we can move it up front. Now, so this part is, well, AD minus BC, negative AB plus AB, CD minus CD, and negative BC plus AD. So this is just zero. Ah, this is just zero. This times, now when we multiply by 1 over the determinant, it just equals 1001. So works. Okay. So we haven't proven that a matrix commutes with its supposed inverse. So we would also need to check that A inverse A is also equal to the identity. So we'll leave that as an exercise. So in general, to find the inverse, like let's say we have a 3 by 3. So uh we're gonna kind of combine two matrices. One is a sign matrix. So, so for 3 by 3, it's this. one is the other is a cofactor matrix. So I think it's called an adjugate. So what we do is for every element of A, we delete the row. So let's say we take the first row, first column. We look at all the other rows. So we delete the first row and first column and look at this matrix. This matrix has like we take the determinant of this matrix. So this is 50 minus 48, which is 2. And then we multiply it by the corresponding entry in the sign matrix. So maybe, so I don't know if sign matrix is an actual term, but we'll just call it that. So then now we take the first row, second column. We look at the 2 by 2 matrix formed by deleting the row and column it's in. So it's called the cofactor matrix of 2. And then we take its determinant. So, I mean, really, you should think of like the 610 on the left of 47, but we're going to multiply by the number in the sign matrix. So this is 4 times 10 minus 6 times 7. And then we multiply it by the negative sign. So, yeah. And then we take this row, the 3, look at its cofactor matrix. So that's 4, 8, 5, 7 by deleting the third row and first row and third column. So this is 32 minus 35. And we multiply it by positive 1. So we do that for all of the entries. So, I'll just do it. So for 5, it'd be 10 minus 21. So that's negative 11. And then it's got a positive, so we leave it. For 4, we look at 2, 3, 8, 10. That's 20 minus 24. So negative 4. But there's a negative sign here. Yeah, there's a negative sign there. So we negate it. 6, we delete its row and its column. We're left with 1, 2, 7, 8. The determinant is 1 times 8 minus 2 times 7, which is, well, like negative 6. The sign here is negative 1, so we put a negative. 7, we delete the row and column it's in, so we're left with 2, 5, 6, like 2, 3, 5, 6. So the determinant there is 2 times 6 minus 3 times 5. And then this is in this like first column, third row. So it gets a positive sign. Like similar, like 8, 6 minus 12 is negative 6. There's a negative sign here, so we put a negative sign. And 10, we delete the row and column it's in. We get 1 times 5 minus 2 times 4. This has a positive sign, and so we just leave it as is. So this is called the adjugate matrix. So we take the transpose of this, which means we flip it over the main diagonal. So in other words, all the rows become columns and all the columns become rows. So here this is 2, 2, negative 3. So we write 2, 2, negative 3. This is 4, negative 11. This. And then we do the same thing here. So this is 1 times 5, 2 times 4. So the inverse is this matrix divided by the determinant of A. So I'm not going to compute this, but that is the cofactor. This is the cofactor expansion way. So, okay, let's just check, right? Does this way align with our 2 by 2? Well, here, our 2 by general 2 by 2 is A, B, C, D. So let's see, right? Uh, maybe I'll write adjunct ADJA to mean the adjugate. Um, so yeah, I think the word is adjugate. Although I was never taught this word when we learned it. So we look at A, delete the row and column it's in. We're left with a 1 by 1 matrix. Rewrite that here. We look at B, delete the row and column it's in. Write the remaining 1 by 1 matrix that goes here. We look at C, its cofactor matrix is B, so we write B. Similarly for D, the remainder cofactor matrix is A, so we write A. So now we take the transpose of this and we multiply by 1 over the determinant of A. The determinant of A is AD minus BC. So adjugate of A transpose. So this matrix transposed is okay. Yeah, sorry. Like the sign matrix here is plus minus plus minus. So this gets a minus sign and this gets a minus sign. Yeah. Yeah, that's important to remember. So this, yeah. So then when we transpose it, we get D negative B negative C A. And like we multiply by 1 over the determinant. So yeah, that's exactly what we said the 2 by 2 matrix was. The trick for 2 by 2, if you want to memorize it, is we switch A and D, and we keep B and C fixed, but we negate them. But really, looking at it, yeah, looking at it from the cofactor expansion way, like B and C actually swapped, but then we had to take the transpose, so it looks like they, have stayed where they are, like they haven't moved. But we have to multiply by the sign matrix or whatever this matrix is called, like the matrix of like this matrix is always alternating, like it's plus minus plus minus, minus plus minus plus, and so on, no matter how big your matrix is. So yeah, this method works in the case of a 2 by 2. Okay, so maybe I'll just leave. So okay, uh, another way to find the inverse is with Gaussian elimination. So the way this works is like let's say we start with this matrix. So we adjoin the identity matrix to the right. So that just means we like write the identity here. So we're going to make perform row operations, so Gaussian elimination, on the matrix on the left until it becomes the identity. Whatever we do to the matrix on the left, we do the same thing to the matrix on the right. In the end, so yeah, so, uh, we'll take the first row minus like -4 times the first row plus into the second row. So like times -4. So this will be 0, well, so 1, 2, 3. 0, 2 minus, so yeah, -3. And, like 3 minus 12, 6 minus 12 is -6. And then we're going to use this one and eliminate the 7 in the third row. So we're gonna take the first row and multiply it like, yeah, add -7 times the first row to the third row. So 0, 8 minus 14 is 6, 10 minus 21 is -11. So whatever we do to the first row, like we do to this one too. So this will be -4, 1, 0. And we did like, yeah, so we multiply by -7 here. So this is -7, 0, 1. Okay. Now, now we look at the second row. We use this as our pivot and we eliminate, we try to make everything below it 0. Sorry, there's a bug. So, uh, so we can multiply this by -2 and add it to the third row. So we'll get 1, 2, 3, 0, 3, 6. And then this will be like 0, then negative, like +12 plus this is 1. So now we have to do the same thing to the matrix on the right. So we added -2 times row 2 to the row 3. So this will be 1, -2, 1. Now we like we're going to use this, the third row, to make everything above here equal to 0. So we can add 6 times the third row here, and yeah, like -3 times the third row to the first row. So then we get 1, 2, 0, 0, -3, 0, and 0, 0, 1. Yeah. So whatever we did here, we have to do on the right. So yeah, so -3 times this. Oh, okay. So like we have to add -3 times it and -3. Yeah. We added 6 times row 3 to row 2. So then, yeah. So finally, we use the second row, which now has a 0 here and a 0 here, to get rid of the entry here. So like yeah, we need to multiply by 2/3 and add it. So on the right, so this will be 1, 0, 0, 0, 1, 0, 0, 0, 1. And like, so times 2/3. So this will be negative 2/3. So let's see, 2/3. That's negative 22/3 plus 6 is 18/3 is negative 4/3. And like 2/3, yeah, 2/3 of 6 is 4, so this will be 1. So assuming I did all my calculations right, the matrix on the right should be the inverse of the matrix we start out with. So like what is it that we're actually doing, right? Um, it's kind of like we did a bunch of row operations on this matrix, and we ended up with the identity. So then if we start with the identity and do the same operations, like they're going to kind of like reverse each other, right? Like for instance, if I call this operation E1, where I add -4 times the first row and to the second row and -7 times this first row to the third row, let's call that E1. This will this can actually be represented by a matrix. It's going to be like 1, maybe -4, uh, 7 or something. Like it'll either be this or this. Can never remember which one. But regardless, it can be represented as a linear transformation. And then we did a row operation to like go from this matrix to this matrix. Uh, and let's say that's E2. And then we did like whatever here, and like uh yeah, and we can do the same thing. This is E3 and so on. This is E. So uh we want to show this is A inverse, right? So question mark. If we do the reverse operations, like we apply E4 inverse to this, to A inverse, to this matrix, and then we apply E3 inverse to this, the result, and then we apply E2 inverse to go from this matrix to this matrix, like to this result, and so on, then like we'll get the identity. So it's kind of like uh and then we keep going. So it's kind of like A, like first we applied E1 to A, and then we applied elementary row operation 2 to A, and then we applied E3, and then we applied E4. So what we like if we go backwards on the right side of our adjoint matrix, A inverse, first we apply E4 inverse, and we get the second to last matrix on the right. Then we apply E3 inverse. Then and we get the third to last matrix on the right. Then we apply E2 inverse. And finally, we apply E1 inverse. So this is equal to the identity. So like, yeah, these are reverse operations of each other. Like we can write, so matrix multiplication isn't commutative. So when we multiply an expression by a matrix, we have to specify, do we multiply by A on the left or by A on the right? Those are two different operations for matrices. If we multiply both sides of this equation by A, we get A equals, so like the A will cancel A inverse since like, well, okay, so we haven't proven it's the inverse, but like, you know, uh, like like if you substitute, uh, so this equals the identity, like, yeah, like if you substitute this in, you'll just get the identity. Like, uh, it, uh, I think I may have switched the order a bit, but yeah, like yeah, if you substitute this, then you'll get the identity. So it's kind of like if I add two to the left, uh, it's kind of like functional inverses. So if I have f of x is 2x plus 3. First, this says first double the input, then add 3. The inverse should do the reverse operations in the reverse order. So the inverse, f inverse, should first subtract 3 from the inverse to undo this, and then divide by 2 to undo the first step. So f inverse should be x minus 2 over 3. So this is the exact same thing.